Good evening, scientists. Welcome to another evening with me, your host, Zio, 205 IQ. We have a few things on the board I'd like to discuss with you today that impact society as a whole, the global future of everything we have here, and of course the upcoming global warming blanket that mankind in its infinite wisdom decided to create. That CO2 thing. But in the meantime, let's go ahead and look back into the past. This is a video about the Mantle melt liquification effect, or event if you want to call it that, and it appears to be induced by the nuclear fission core of the planet Earth. And how do I know that? Well, looking across the ice ages for the past 2.4 billion years and the average surface temperatures of the planet, we can see that there is a active nuclear reactor in the planet. And from that we can extrapolate several different points. Two things. First, that it's cyclic. It gets hot. The critical, it just goes basically straight up after it reinitializes, after cooling down. And then it goes up, it peaks, and then it planes off. And it looks like it's been planing off in a really long process here. This is over 200 million years, and this is 260 million years. So over 260 million years, it's been planing off. Well, it sunk and then it planed. But that little thing right there, this graph, if you can look at that, has a progressional thing here. Well, it comes right here. So is that just a fluke, or are we looking at something different? And we need to graph that as well. So what's going on inside the planet Earth? Well, first thing, let's look at the facts that we have presented so far. When the surface temperatures get low, it indicates fissile core initializations beginning. So that's the same thing with the Oklo natural nuclear reactor in Gabon, Africa. That one does the same thing, or did the same thing. I think it's still reacting. It got cold. There were 4 uranium deposits in the Gabon, Africa strata there, and they would react, and then they'd cool down. They'd react to cool down. We found uranium depleted there, and we found plutonium byproducts, plutonium radionuclide byproducts, decay products in that area when we examined it. So now, why do I say it's nuclear? Well, if we look at the maximum rate of uranium, now you see right there, way back in the beginning there, when the system was brand new and it was balanced, look at that criticality curve. It matches that criticality curve almost exactly. And it says to me that what happens inside the core is basically we have this natural nuclear reactor, and we have 2 things that are going to affect how it works. First thing is going to be its cooling, of course. Well, yeah, it's cooling. And then second will be how much uranium, in this case, according to the math and the effects here, you have to have uranium-235 in particular for the neutrons that are being emitted to create a fissile reaction like the one seen here, which I'll hold up there for just a minute. A lot easier than trying to copy paste sometimes. Okay, you can see here what happens is the reactor gets cold, it heats up, and then it planes off as the mantle, liquid rock cools off that reaction and takes the heat to the surface, which is transferred to the oceans, it's transferred to the surface crust, and then from the oceans to the atmosphere, from the atmosphere using cyclones and hurricanes to space. And that's kind of like the whole process on how our nuclear fission furnace, which is the Earth, gets rid of its heat and keeps running. Now, I did notice this plane here, this 75 degree average surface temperature plane. Unlike Venus, which follows a different plane, Venus's surface temp is like 900 degrees C, 800 degrees C. And you can see here on this graph, which I will now hold up, you can see on that graph, that line right there. That line right there. And that's called... It is called FGR with burst. So present work. So right there, if we looked at that and we looked at the surface temperature of Venus, we know that Venus has a bunch of uranium and it's currently, as a fission reactor, it's in a burst mode. The surface temperature is, like I said, 800 to 900 degrees C, and it has a dense atmosphere, so it has a large iron core that is rapidly spinning. It's the atmosphere of Venus is thick and dense, which means that your flux lines, as they travel through that atmosphere, are kind of holding in that atmosphere, and they're not letting it escape. And that, combined with no surface water, means that this silicon fissile reactor is running in a burst mode. Like, it's sitting there balanced, but it's not gone into a criticality. Let's see here if we compare these two. No, it's being held at like 65%. You know, Einstein said it best: God doesn't play dice with the universe, and he's not playing dice with Venus. Venus probably won't blow up. Earth, on the other hand, we have this curve right here, which I'm a little worried about. And, well, I don't know, not too worried about it, because, you know, Mars, when its core either stopped spinning or got too small to really create a surface envelope or magnetosphere, it just got cold. You know, Mars's surface temperature is very cold, and it doesn't have active. I don't think the volcanoes are active at all. So I mean, they have dust storms now. So it's basically a dead world. The internal fissile furnace, if it is still activating, is very, very weak, and probably doesn't follow our curves at all. Now, what I was saying about this peak here at 75 degrees average surface temperature, that is because we have water here. Venus doesn't have water. So like I said, their surface temperature, 900 degrees C. We don't want that. Now, admittedly, it has a really high atmospheric content of CO2, sulfuric acid, things like that, but we don't want that here. So water, in our case, we have a water-cooled nuclear fission reactor in the core, or that's what the Earth is, essentially. However, according to this graph, the core is getting physically smaller and probably slowing down. But if you look at the diameter of a spinning sphere in a liquid and how it creates convection paths from that interaction, you can see that even if the sphere was physically smaller and spun faster, it would have to spin a lot faster for it to make up the difference in the diameter change. And why do I say the diameter is changing? Well, let me show you. This, you fellow scientists out there, you've probably never seen one of these rocks. This is a Mantle core sample that I happened to come across in my travels, and it was at a drill site that was approximately 20 miles deep. A lot of you are like, what? 20 miles deep? That's totally, there's no published hole that deep in the crust, blah, blah, blah. Exactly. There's no published hole. So this was a private deal. So you take my word for it. This rock's special, and I'm going to describe it to you and describe why what is in that rock is so special and why it describes this curve, this long cool down curve right here, which defines that the core of the Earth is physically getting smaller because it's being shaved. How is it being shaved? Well, when you take steel, it's iron core, but it's steel. You got carbon, you got cobalt, you got all these different metals, and then you got the interaction layer between the inner core and the outer core. So because of the quasi-crystal being how it's formed, and that's essentially what these are inside this rock. Anyway, so let me tell you the story there real quick. I was at this drill site. I was one of the few outside scientists, I guess, to visit it. And I was young and unofficial and all these other things. And so they were just like, yeah, whatever, kid. come on in. And I looked down on the ground over by the management office, and there it is on the ground. And there's like a pile of these really weird rocks. I'm like, what are those? And I was a hobby geologist, scientist. I grew up, I loved rocks. I lived in rock shops. I lived out in the field. Whenever I see a rock outcropping that was really cool, I'd go check it out. And in this case right here, I looked down on the ground right outside the office there, and I'm like, that is the strangest rocks I've ever seen. And I'm like, okay, well, it's not like it's in a special, quarantined area. Well, these are pretty cool rocks. So I grabbed one and I looked at it, and I'm like, what are those? And it was a foamed basalt, so silicon in a basalt area. It kind of looked like a moon rock because it looked like homogeneous powder or something that's been pressed, but it was foamed rock, and volcanic probably in origin. However, there were these quasi crystals in between the junctions, where the foam inside, where the junction points between the bubbles are, they're closed cells, and at every junction point there was like a different size, little hard, angular shaped iron, cobalt, and some other metals ball, and I was like, what are those? Those are bizarre. So I'm like, this is cool, and years went by, and I thought about it, and I'm like, those are cool. And then recently, in the last 10, 15 years, quasi-crystals, that was about 25 years ago when it really hit the news. Quasi-crystals hit the news. And basically what a quasi-crystal is a reordered, structured, extremely hard, extremely dense, almost as dense as you can possibly pack those particular atoms in a quasi-crystal formation. It's almost like a pentagram-like crystal. It's not really hexagons, more like pentagrams. And pentagons. And here's just the basic formula. It just states that you're taking a material and reordering it, structuring it to create a new material of higher density. So it's a reordering of the atomic or the molecular structure to end up with these quasicrystals. So the quasicrystals, most likely we have. Long story short, it sounds like to me, even though the books say we have a molten core, at some point in there's going to be a solid core too, either due to compression or whatever effects that generate that. And there's probably going to be some transition layers. And how you create quasicrystals generally is you take a rotating drum or a rotating sphere, and you gouge it with some like a sharp finger. And there could be big, giant iron crystals that are floating around that core as it spins, and every once in a while they reach in and they go and they just, or they, there's a whole bunch of them, so they're constantly like hitting it and then recombining depending on their size and whatnot. But when they gouge it, they're gonna shave off these quasi crystals in streams. It's gonna be like when the claw hits the rotating sphere of the core, it's going to go and you're going to get this stream of material from that core, and inside that stream you're going to have these quasicrystals. And these quasicrystals are being carried up by the magma and the heat and the convection to the surface, and they're depositing in the surface and also floating throughout the magma itself. So all your magma samples that come up in the right areas, I would say, because these are going to follow paths of least resistance, your centrifugal forces, your kinetics, all your other things, and of course magnetic fields. Now, because of their orientation, you ever see how magnets stick to each other? Well, slightly magnetic materials will do that as well. They'll kind of clump up. And I think in the presence of this giant magnetic ball in the middle, it's probably going to keep most of them from escaping. So it would have to be a very specific location and a very specific event for these quasicrystals to make it to the surface anyways. Anyway, so I found this rock, and it had these quasicrystals in it, and I'm like, wow. And then, of course, this is years later, I saw this graph, and how does that explain this graph? Well, basically, how fast a nuclear reactor cools down is based upon how fast you can move the heat away from it. So if in the past we had a very large core that's spinning at its max Q speed, and you had a reactor heat up, a molten silicon reactor heat up, as it cooled down, you see this sharp cool down here? That means that thing was working great. And look at that cool down right there. Bam! You see this one was in waves, so we were probably traveling. See, that's 350 million years ago. It's 400 million years ago. So perhaps that was us traveling through. Let's see, 450. So that could be, yeah. This could be this pattern right here. This wave can be our solar system traveling through the equatorial plane, the equatorial galactic plane. So like one pass like that. So we go through it once, maybe through it again, and that changes the spatial compression rate of space, and it changes the nuclear rate over a period of time, as you can see here and there. And this wave here was in the actual graph math. So just a little bit though, just a tiny wave, just enough to show us. And anyway, so that's not what's important. What's important is the spin down. So you can see this one, it cools down really, really nice. This one has a little bit more trouble. This one cools down but then reinitializes, which is something that we see in our current reactors when we're playing with them, turning them on, turning them off, turning them on, turning them off, wrapping them up, wrapping them down. You can see that it started to cool down, but since this is, I guess, the dispersion pattern or the dispersion amount of uranium, perhaps it changed between 260 and 200 million years ago. Perhaps there was an event that added additional uranium to the mix. And if you added more fuel, that's how you'd reinitialize like that without having a series of other events that would follow that same pattern. Like we didn't see like this dip is good. And also you can see that the core changed right here too. Look at this long period here. That is really long. It stayed up for 200 million years. It stayed up for 200. Let's see, 100 and was that about 100 and about 200 million years before it dumped out again. So most likely at 200 million years, right around that time, the Earth was struck by a large meteorite that contained a lot of uranium. And out there in space, uranium, is going to be pretty common out in the asteroid belt in places, and due to certain events such as red giants exploding and things like that, and of course other planets that explode as well. Because there could be that effect on other planets where you get a runaway reaction, the reactor can't cool itself off adequately, and the core can be shaved or damaged or whatever, and then of course a planet would explode. These planetary explosions, we first saw that effect out in space with one of our spy satellites. We were looking at the Earth with a gamma, very specific frequency gamma. I think it's 0.7 mega electron volt, either 0.7 or 1.7, either way. And it detects the unique signature, gamma signature, of a nuclear weapons detonation. Uranium-235, plutonium, blah, blah, blah. It's a very specific gamma signature. Well, one day we lost gyroscopic functionality and control of that satellite, and that spy satellite, swung around, and now it's like pointed out at space. And while it was still viewing the outer reaches, it looked out into space, and the scientists that were monitoring that satellite saw all these gamma signatures, and it wasn't just a fast gamma pulse. These were explosions. And they were like, wow, there must be like a bunch of nuclear wars going on all over the place. However, the yield that was coming back from these interstellar explosions that they saw were huge. They're way bigger than anything that man could make. So that can easily be explained by a runaway fissile reaction inside a planet, where this curve doesn't have the adequate cooling, where the planet loses or reaches a point at which it loses its water, kind of like Mars, but it's further in or has more uranium making up its fissile core. And of course, it's because of Newton, because things balance out, because all things are pretty much equal when it comes to materials and how they lay out and stuff like that, you would have a situation where a runaway reactor could indeed cause a planet to explode from the inside out. And there's proof of that in our asteroid belt. We're actually sending a probe right now out into the asteroid belt to examine a planet core. Now, when I look at photographs of that planetary core, it looks like it's been forged. Like on the outside, a bunch of stuff exploded and went crunch. Kind of like you're taking a Skittle and squeezed it between your fingers when it's hot or warm. It just kind of like deforms. And the deformation that I see on that planet core that's out there, and the rubble and debris that surrounds it, you know, the asteroid belt itself, looks like it very well could have been formed by a criticality, a fission criticality. And could planet Earth suffer such a thing? Well, not necessarily until we lose our water, but that's water by itself, as the Japanese can tell you, water by itself is not enough to prevent a cascade criticality. It's just not. And in the case of large reactors, you could have a criticality start in one spot and then spread across. I mean, you can see how uranium-235, you know, it emits 3 neutrons after just the first split, and then it goes to, what do we got here? 8. We have 8 neutrons, so it goes from 1 neutron to 8 neutrons. So it's a runaway reaction. Now, because of convection currents and flow of the liquid portion of the mantle, and because of the core spin, you shouldn't have any banded formations of uranium-235 forming. However, if the spin and the scale, the physical diameter of this core changed considerably, as you can see, it has probably changed here, and for it to reinitialize like that, it would have to be additional uranium being added to the envelope, making it into the mix, or being released by the core outward. But as you can see, it's been so stable for so long, it was probably an addition of more uranium to the core approximately 200 million years ago, and then of course it spun up. Now, you can see when it spun up, it stayed up longer. So most likely, the core, when it got hot again, it's gonna be, well, of course, the entire time it's shaving, you can see the curve here gets longer and the angle changes, and that's because the core is getting shaved and losing iron. Now, there's a constant rain of iron from the sky, but how much of it makes it back down in to the core from the subduction zones on the crust? Not very much. I mean, not enough, I don't think. And you know, how would you reintegrate quasicrystals into the core that have been thrown out? Well, they should be able to reintegrate where the highest friction points and highest friction zones are. You know, if they bounce around enough, it's just going to eat them, kind of like how like a snowblower can just grab stuff and then make a big pile off to the side. Well, this one's going to be more like grinding it into something. Anyways, so let's get back into what we're talking about here. For all you science buffs out there that love math, this is the uranium transition equation from the force, and you have the primary uranium, and then of course you have the little graph right here. The problem is that I'm seeing is that at 60 degrees, approximately, see this 60 degree line? Look, it even does it right there. Even after the addition of uranium, right approximately 60 degrees, it reinitializes the fissile reactor inside the planet Earth. And that's one of the things. We are at 58. Actually, look at that. I didn't draw that right. This is, sorry, I dropped my pen. This line should go straight up like that, because we are at 58.2. And that's because of the industrial age. That's because of CO2 in the atmosphere. That's because of all these things that we do as a species to change the environmental atmospheric envelope. Now, a lot of you who've been monitoring the oceans and the weather and other things like that may have noticed that, we're getting more cyclonic activity across the Pacific. We're getting more hurricanes. We're getting all these events out there in the oceans, and those events are directly related to solar thermal radiation. But remember, the sun has been in a solar minimum for a while, and it's just now waking up. We're approaching max Q on the sun as well, maximum production. But it's going to be a few years before it hits that. About 5 to 10 years, I believe, so 11-year cycle. So during that time period, since we know that we're spinning up here, when we hit 60, the core is going to reinitialize, kind of like what it did here, and the surface temperatures are going to jump. They're going to go from 60 degrees, they're going to increase by 15 degrees, and that heat has to be dissipated out into space. Now, we recently had the Tonga volcano, and there's probably going to be more like that. Those are volcanoes that are in the ocean and that erupt under the water and go into the atmosphere. They release water vapor and other vapors into the atmosphere that holds in heat, and other gases that holds in heat. And so they're expecting, as opposed to a normal volcanic reaction from a volcano where it would bring the temperatures down, they're expecting a 5-year increase in temperatures. And you can see here, we are right at the core. The core is already initialized. It's spinning back up right now. The 60 degrees, you can see it initialized way down here, but at 60, let me see here. Well, at 60 here, it turns on and peaks out. If we peak up to 75 again, that's going to bring up the global surface temperatures like radically, like a lot radically. And I don't think that we as a species or the oceans or anything, if you count the CO2 as an issue, when we hit 600 parts per million, we're at 400 right now. When we hit 600 parts per million, we got a real problem. So let's say this reactor spins up, and during this time period right here, we have a shift. So I'm thinking right here, from there, and there, it allows for this event to take place. And it's not a really good thing. The Mantle liquification effect event is not good for the majority of the population of the planet. In every single religion and society, there is a flood legend. Not a myth, a legend. They tell these stories as if they're absolutely real. And there's enough evidence across the planet to show that ocean waters have washed across at rapid speed and reshaped the land all over the planet. But then the oceans receded. Or was it just one pass? That can definitely be related to what I'm seeing from the 2011 gravity map survey and from this event. You take those two things and you end up seeing that, these diagrams right here, you might recognize this picture, but this is the gravity picture. So when I describe it here, one of the main gravity high points, or the densest part of the surface of the crust of the Earth, it's in Siberia and just north of Australia. So if you were to liquefy, or I should say change the viscosity to one of a thin viscosity of the upper mantle, I think you're going to have this full plate shift where it can balance out now. Now, over the past, 200, honestly, over the past, over the past 200 million years there, even if it was liquefied here from, I guess that's going to be the past 75 million years. In the past 75 million years, just from crustal tectonic plate spreading, these plates, according to scientific models, have moved around, which means the balance, the density, the material balance how the materials are on the crust, the density. Where's the densest points? Those have been repositioned, not necessarily via. It's kind of like driving a wedge. Ding, ding, ding. You put another wedge in. Ding, ding, ding. And something can move. But if you take all the wedges out, then of course that's going to move back. But basically, that plate spreading down on the bottom of the ocean and tectonic spreading, it's going like that. And it's like a conveyor belt that's pushing these land masses out of balance. When this liquefaction event occurs again, it's probably going to be right after the we reach a viscosity of the mantle. I mean, one day it's going to be holding, and the next day the whole thing is just going to break loose. I mean, literally like overnight, it's just going to go boom. And according to all the math, the Earth's spinning 1,000 miles an hour. The land masses will change orientation and direction, whereas the wind or the air kind of stays in place, and now the land's moving in a different direction, and now the water, which was there, and it can move in a different direction as well. So the land can do this underneath the water, and it can also do that through the air. So if your land shifts like that on the planet suddenly, well, the water is going to carry across that area. When I looked at the gravity map survey from 2011, I saw that when the full crustal plate shift, the global crustal plate shift occurs due to the mantle melt liquefaction event itself, the ocean, in this particular case, Siberia and Australia are both going to go equatorial. They're both going to go whoop. Siberia is going to drop, Australia is going to go up, and that's going to be balanced kinetically, centrifugal forces to the equator, to the spin. And of course, it's not going to be perfect. It's going to wobble. And that might be how Siberia ended up there, is when it did solidify, it just happened to be on that part of the sine wave, as it rocks. So these things are going to rock back and forth. And that means there's going to be some parts of the Earth that will be unlivable. Now, is it going to happen fast? Well, you can see this curve right here, which is kind of like, it's kind of relaxed a little bit, and that's because of the core shave. It's not gonna spin up as fast. Or I should say, no, because of the core shave. Sorry, because of the core shave, it's gonna spin up even faster, and it should go straight up like these other ones here. Should just go straight up, and also with the addition of that uranium back 200 million years ago. Because of that, when the core liquefaction event occurs, the whole mantle is just gonna, the whole crust is just gonna break loose, and Siberia is gonna bounce out. But they're not just gonna go to the equator and stop. They're gonna wobble like this, and they're going to induce a wobble orbit of the Earth, where the Earth is going to travel out of its near elliptical or perfect orbit, and now it's going to loop out into outer space, more towards Mars, over and over and over and over again. And every time it does, it's going to have less solar energy. It's going to be away from the sun more, so Earth as a whole will receive less thermal radiation from the sun. However, since we're in an uptick here, I think that'll be a bit of a relief in some respects. But I mean, is it going to induce a global ice age? Well, no, not if we're at a peak. If we're at a peak, it won't induce a global ice age. It would not be possible. And also, if this runs away even further because of the reduced size of the Earth's magnetic core, we already know from monitoring the fields even over our lifetime of the magnetosphere of the Earth that it's getting weaker. And we also know that we have a pole shift coming too. So every 100,000 years or so, according to sandstone records of layers of sandstone, we know that the North Pole shifts. Either full shift, north-south, 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 every 100,000 years. That's roughly. I think it's 103, 105, something like that. That's going to take place at the same time. So we have a bunch of things that are happening at once. And you're going to end up with a wobble orbit of the Earth, which is going to make hot and cold, hot and cold. It's also going to cause this thing while it's in this melted or liquefaction event, it's going to make it so this thing just goes all over the place. I mean, it's just going to go like that. It's going to rock and roll. So there's going to be places where water is literally going to wash over an area over and over and over and over again. And it's just going to erode. And there's going to be oceans. There's going to be oceans over places that are now land. Now, admittedly, due to plate tectonics, we have some upthrust, the Rockies and things like that. However, if suddenly you have basically the ocean moving over the land, it's probably going to cause an issue. Now, looking at South America is interesting because I think that due to the mountain range here over in the Chile area, I think it deflected the water the last time this happened, which, would be millions of years ago. But I think this has happened before, and the last time it happened, it deflected because we have a biodiversity here of animals, flora and fauna and things like that survived and then spread out. It seemed like the closer you go to the backside of this mountain range, the more diversity you have. Whereas you go here, where I show this arrow going across the Rockies or the Central Plains, basically in between the Mexican mountains and the Californian and Colorado Rockies, is basically going to wash over that and then up, I guess, up into the Great Lakes area and right over the top, or maybe just up a ways. I mean, they're talking about 1,000-foot high waves. That's like the speculation is, we're going to have 1,000-foot waves traveling at 1,000 miles an hour. Maybe. But that should be the direction. When this thing goes like that, the ocean's going to go up and the landmass is going to go down, and almost everything will have the chance to be underwater if they're in the way of that water. So when this does this, click, water could, because it's not going to, it might be pretty fast. It might be pretty fast. That guy was predicting that it just goes liquid and the whole thing breaks loose one day. But the way that when you heat up like a putty or a plastic or a metal or anything like that, and that's essentially what we're dealing with is a sticky mantle upper layer, it's going to melt slowly. So I think more likely it's going to be like kind of a slow, kind of gradual. Eventually it'll settle out at the poles. But once again, I'm gonna have to trust Einstein's musings when he said God doesn't play dice with the universe, and I don't think he's going to play in that respect with wiping out the human race. I think that we're probably okay, but it's still going to be a danger to many coastal communities such as Florida. Florida is 40 feet above sea level. Man, they need to, I don't know, they just need to move everything out of Florida. And everybody who owns land in Florida is just like, I should buy that lot. No, I wouldn't buy land there. Move closer to the mountains. I mean, in the lee of the stone, not on the west side of the mountains, but the east side. Put a wall between you and the most likely place for this water to come at you. When will it happen? Well, it could happen pretty soon, and if it does, like I said, we'll have a crustal shift, and that crustal shift will induce a wobble orbit, which will cause this to kind of do that during the entire liquefaction or mantle liquefaction. And I realize that the mantle's already a liquid anyway, or it's kind of a liquid. It's liquefied. It moves. But imagine if the viscosity went to like water, and that, or if you had like a layer where you had just so much liquefaction that there wasn't anything slowing that down or preventing it from going in a different direction. It's not going to lock into the spin of the core because it's too big, but the core does induce the convection currents and things like that of the magma. So let's see if we've covered everything on the board. All right. I think we pretty much got everything on here. There's some speculation. Nuke criticalities: when fissile core cannot cool itself, a criticality or meltdown occurs. We already know this because we have nuclear reactors that melt down if they don't receive proper cooling. In the case of our small, super hot, zirconium rod-fed pellet reactors, that happens pretty fast as soon as you lose cooling, the flow. But we're not talking about a stop of that. We're talking about a slowing of it. And you get this curve right here. I think that curve was caused by two things. First thing, we had an addition of uranium approximately 200 million years ago, and also the core itself is shaving itself by means of these quasicrystals up magma channels into the crust. So the physical core itself is being shaved or lathed, and these quasicrystals can survive the melts and deposit themselves in the magma. And that's essentially what this is. This was a magma rock with quasicrystals in it. And let's cover some of the other stuff I got on the board. So Venus has a thick, dense atmosphere. It's because it has more uranium. It has a hotter core. Is it a faster spin? It can be a faster spin and physically be smaller, because the faster the core spins, the more flux lines there are interacting with the atmosphere, holding the atmosphere against the surface of the planet, ending up with a denser, hotter atmosphere that won't release heat. Okay, very active core, large would be a question mark. This one's very active, but I think due to its it's going to be larger because it's closer to the sun. Most likely, it's going to have a larger physical iron core. That's I don't know though, because apples, are all about the same size. You ever notice that? If we compare planets to apples, well, apples are all about the same size, right? Planets are all about the same size. I think there's going to be a maximum Q spin up, like when you're forming a planet, that like it'll shed the extra stuff, and only what can stick within a certain volume at a certain spin rate at a certain distance from the sun is going to form. You're not going to get like planets of these compositions, and since your primary composition across the universe is going to be silicon anyways for most of these inner planets, your cores are all going to be about the same size. Your planets are all going to be about the same size, plus or minus, just like apples. Planets are like apples. Some are big, some are small, but they don't get really, really big, and they pretty much, they can get as small. They can get really, really small, but generally the majority of apples are the same size. Well, generally the majority of planets are going to be about the same size too, due to spin and materials and density and elasticity and the strength of the materials and things like that in compression. Well, all right, Earth has less uranium in its envelope, obviously. It has a cooler core, a slower spin, a smaller core than Venus, I would say. But it could be, it's going to be small. It's going to be physically smaller due to its proximity to the gravity well. So we can say that Venus has a bigger core than Earth, and Earth has less uranium due to proximity effects, or proximity effects to the gravity well of the sun. Smaller core, but it has water cooling, whereas Venus obviously doesn't have water cooling, or it got so hot during a runaway reaction that it vaporized its oceans, which are now stuck in the atmosphere. And that's, honestly, this is a fission reactor. It could go critical and just keep going and boil all the oceans, and that goes into the air. So that'd be really, really bad. If we could avoid using or producing more CO2 that created that heat blanket, we're at 58.2 degrees global temperatures. When we hit 60, it's going to initialize 60, 61 right there. It's just going to take off again, and it's already on its rise up. So we know that the core is active already, and that's, I guess. Oh, look at that! Look at that. I drew the wrong curve. Okay, that was the other speculation. This one, we can actually start. We can just connect the dots here. We'll just do this here. Actually, we do that like this. Ding 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 ding. Right down like that. Okay, that line makes a lot more sense. Sorry about that. I'm sure there's some scientists out there going, "Why did you draw that other line?" Oh, that was from another theory, the last board. This one you can see. We have used up some of that boosted uranium input, but there's still more uranium now inside the Earth's fissile reactor than there was here. Here, you had to get really, really cold, and this shows you that the same amount of uranium-235 was present in the fissile reactor of the Earth way back here, and then there was an addition, and then we used some over a long period of time. This should explain the longer burn, or the longer reaction, and then we get a curve up, and actually it looks like we're active right now. So if we're at 50, let's call that 55. 55 is when it initialized. So that's 5 degrees. Globally, that was 5 degrees warmer when it initialized there. We're now at 58. So we're on our spin up. Now, depending, since we're ramping up, we're gonna go straight up to 75. And then, of course, we have the water. So we'll probably cap out like here. As long as we have water, we're going to cap out here. So I'm not too worried about the planet blowing up, but I will say that this is a global warming emergency in the sense that we need to find a better option for powering our industries and going out there and making things move. There's got to be some other options. I've seen some out in the industry, and I'm just like, why aren't we using them? Either way, when we reach 75, we're going to get this mantle melt liquification effect. And, that coincides with some of the things I've been seeing in the news. For example, we're trying very hard to put a global satellite network internet up right now. So everybody can use their phones, access the internet, do all that stuff from a, non-ground based communication system. I think that the entire communication system is modular and it can just talk from the heavens down. It's heaven's web, and I think that's one step of progression. We did they did 9 launches. Now, could this be just a rollout similar to how the cellular phone companies have put cell towers in everybody's neighborhood and nobody really cares? Maybe. But let's look at our attempts to get to Mars and the conversation that the president had with the head of NASA when it came to getting back to the moon. That conversation went something like this. The president says, so, thought about going to the moon. What would that take? And the head of NASA laughed. Physically, he did like Santa Claus. Ho, ho, ho. And of course, the president's like, let him talk. And the president of, the head of NASA says, well, it would take a lot of money and a lot of logistics, a lot of people. We'd have to tool up, but primarily we're missing the money. We're missing the funding to be able to get back to the moon. And the president replied, well, what if you had the money? What if I could get you that money? Would we be able to get back up there? And I think he said yes, or I'd have to work out the details. So here we are 3.5 years later since that conversation, and we just sent a rocket to the moon, a full lunar lander to the moon, under almost no media fanfare. It's like the media basically ignored that we were going to the moon. I mean, I saw some stuff on YouTube about it, but it wasn't like it was, 1969 where everybody's like, moonshot, 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 or 1970. It's just like, back in the day, that was like a really huge thing. But now, with SpaceX, 9 heavy boosters last month, or nine shots up into space last month. It was a lot. It looks like they're moving the mission to Mars to 2030. I would recommend not going to Mars initially, just because there's it's all those perchlorates. The surface is basically made of rocket fuel, which is good. I mean, that means you have endless rocket fuel if you go up there. However, it's bad because it's a dust and it's in everything. I mean, it's going to be like the moon dust. The moon dust, same way. All the astronauts are saying, man, that moon dust got into everything. The filters were dirty. It was all over our suits. I mean, it's just terrible. Same thing's going to happen on Mars. Mars is basically a death trap right now. But I may have a solution. And I'm going to have to do some more heavy equations to show you how to do that. But what if I told you there's a strong possibility to generate a form of travel that would be better than rockets? And I'm going to make a video about it, but it's interesting to see the possibilities and the simplicity of the technology. We already have a lot of the basics, and it's interesting to see that we haven't gone that direction yet. But maybe it's just a lack of knowledge in that direction. So, but either way, I hope you enjoyed the video. This is, I think I covered everything on the board. There's nothing that I really didn't go over. There's the wobble when we hit 75. The stabilization from the oceans at 75, as long as the fissile core is reacting. The longer curve due to two things: increased uranium deposits into the mantle reactor, and also the shaved core, which is evident by quasicrystals in basalt, foam basalt, in the subduction zone up in the Pacific Northwest where that hole was drilled. Either way, this is this is pretty out there, but it follows all the principles. I mean, there's Newtonian physics here. There's nuclear physics here. There's geology. What else do we have up here? We have plate tectonics. We have astrophysics. We have magnetic field study. We have wave propagation theory. Well, we got thermodynamics. Is there electrodynamics here? Well, it's primarily just thermal and nuclear breakdown and whatnot. But either way, let me make sure I covered all my graphs. Did you see this one? Yeah, you saw that one. That was for Venus. That shows that it's in a burst mode at 900 degrees C. That's why it's hot. Let me see here. Did I get all my papers here? Okay, you see the quasi-crystal formation here. Basically, you're just reordering the iron and steel and whatever. It's iron, but it's mixed with other stuff. It's not just a ball of pure iron. Pure iron wouldn't survive there. It needs to be like a hybrid, a forged hybrid. Planetary formation. We went over that. That's pretty cool. How based upon centrifugal forces, materials themselves, gravity well, and all this other kind of stuff, you can only make planets in normal space around G-class stars, which 99.9% of all the stars in the whole universe are those. So all your planets are going to be about that size too. And it also explains why when we looked into space and we saw all these giant planetary scale nuclear explosions, now we can begin to define why they would explode in the first place. I hope you enjoyed the video. Once again, I am Zeo205IQ. I hope you subscribe to this channel. I hope you comment down below and let your smarts come out and let the world see them. And then, of course, give me a like button right there. Just give me that thumb that like and smash the subscribe button, because that's what you got to do. You got to smash it. And we will see you in the future when I go into describing how we could get to the moon, how we could get to orbit, how we could get to Mars, how we get to these places, and may not have to even use what we would consider standard rocketry. It's a totally different type of technology. Tune in. I'll make that one as soon as I can. I think this was a lot better this time around, so if any of you watched the previous version of this video, that video, it just had so many sound problems and video sync problems. It was almost like it was a train wreck, and I just didn't know it. As you can see, I have better audio now, so you're going to be able to hear everything I say. We have video now. I wouldn't mind stepping up the quality of the video, but of course that comes with sponsors such as yourself. If any of you want to sponsor me, I have a Patreon link on, some of the videos. I'll put it on this one too. And that allows me to get better video equipment so you can see what's on the board better. Right now you're viewing it at a base 720p. I wouldn't mind getting like a 4K. That'd be great. 4K, the same style. And now we have our audio sorted out, so you should be able to hear everything that I'm saying. And hopefully the audio, I have 4 channels running right now. So one of those 4 channels is going to turn out great, and we're going to be able to at least communicate better in this platform known as YouTube. So thanks again for tuning in. Once again, comment, subscribe, smash that like if you love it, and we'll see you around. Bye now.